two level system where n equal to n1 plus n2 particles is distributed among the two energies E1 and E2 respectively. That means n1 particles are there in energy level E1 and n2 particles are there in energy level E2. The system is in contact with a heat reservoir at temperature T. If a single quantum emission into the reservoir occurs, population changes from N2 to N2 minus 1 and N1 to N1 plus 1, which means it goes from N2 to N1 rather, and N1 is much larger than 1, N2 is much larger than 1. Obtain an expression of the entropy change of the two level system, the reservoir, and finally, from A and B derive the Boltzmann relations between N1 and N2. Okay. Problem number 19. So, this is a two level system E1 and E2, there are N1 particle and N2 particles, and suddenly it goes to N2 minus 1 and here we get N1 plus 1. This is the process that quantum emission is talking about. Now, question is obtain an expression for the entropy change of the system. So, the entropy of this previous system, let us say it goes from A to B. So, entropy of the system A can be written as S A, which is nothing but K B L N W A, where W A is total n, which is n factorial by n 1 factorial and n 2 factorial. Where do we know that n 1 plus n 2 equal to n? Entropy of S B is K B L N W B, where it is n factorial again by n 1 plus 1 factorial and n 2 minus 1 factorial, where again n 1 plus n 2 equal to n. Now, what is the entropy difference? Entropy difference delta S is nothing but S B minus S A, which is K B ln n factorial by n 1 plus 1 factorial, n 2 minus 1 factorial minus K B ln n factorial by n 1 factorial and n 2 factorial. So, therefore, taking K B common, ln we can write as n factorial by n 1 plus 1 factorial, n 2 minus 1 factorial multiplied by n 1 factorial, n 2 factorial by n factorial. This cancels each other and we get n 1 plus 1 in the numerator and n 2 in the numerator, n 2 and here n 1 plus 1. So, that will be the entropy change of the system that we get. And now, we have to see the second part of the question, obtain the next entropy change of the two level system and the reservoir. Second part of the question is that how to calculate the entropy of the surrounding. So, this was the entropy change of the system, two level system, and we have to calculate the entropy change of the surrounding. So, now you know that entropy change of the surrounding is it does not matter whether the process is reversible or irreversible, and there were the total energy of the system earlier, let us say, was E A, which was n 1 into E 1 plus n 2 into E 2, and now energy of the system B is n 1 plus 1 into E 1 plus n 2 minus 1 into E 2. So, therefore, the change in the energy of the two system is E B minus E A, which will be given by n 1 plus 1 E 1 plus n 2 minus 1 E 2, is it n 2 minus 1 E 2 minus n 1 E 1 minus n 2 E 2. So, therefore, delta E is E 1 and minus cancel each other. So, it will be E 1 minus E 2. Now, that is the change in energy, and you know the change in energy and change in heat is same if the system if the work done is 0. So, I will just remind you that du equal to dq plus dw. Now, wherever there is dw equal to 0, the change in energy is equal to change in heat, and now entropy can be written as dq by T. So, let us say the temperature of the system and surrounding is T. Therefore, delta S of the surrounding will be delta E by T. So, that is the okay, by the way. So, this is the energy received, this is the energy change of the system. So, therefore, energy change of the surrounding is E 2 minus E 1. So, it is E 2 minus E 1 by T will be the entropy change of the surrounding. Now, coming back to the third part of the same question is that from A and B derive the Boltzmann relation for the ratios of N 1 and N 2. Okay. So, now the third question demands that we need to show the relation between this energy and entropy. Now, you know that the distribution of particles in different levels follow Boltzmann distribution anyway, but here the question demands that we show the Boltzmann distribution itself. But now, for that we have to compare the entropy that we obtained from this energy calculation and also from the calculation of the W's. Now, in order to show the relation between them, we have to assume that the process is reversible, because if we assume that, then only we can say that the entropy change of the system is nothing but E 1 minus E 2 by T. That means, the change in heat by T. If the process is not reversible, remember the delta S is dq reversible by T. It does not matter for the surrounding though. So, that is why for the surrounding this result is okay. However, for the system this result will not be okay if the process is not reversible. So, assuming that the process is reversible, because without assuming that we cannot even do the calculation that is demanded. So, assuming the process is reversible, we can write the entropy as that, and then we have already obtained a relation of entropy as you can see here Kb ln N 2 by N 1 plus 1. So, Kb ln N 2 by N 1 plus 1 is E 1 minus E 2 by T, and therefore, ln N 2 by N 1 plus 1 is E 1 minus E 2 by Kb T. So, therefore, N 2 by N 1 plus 1 is e to the power E 1 minus E 2 by Kb T, and since N 1 is much greater than 1, we can write N 2 by N 1 is equal to e to the power minus E 2 minus E 1 by Kb T, and that is nothing but the Boltzmann distribution, where if you remember that N I is proportional to e to the power minus E I by Kb T, and therefore, N I by N j will be e to the power minus E I minus E j by Kb T. That is the Boltzmann distribution, which is exactly the one that is on the that is given there. Okay. So, going to the next question now, prove that the maximum value of W is when N 1, N 2, N 3 all are equal and N by R. So, this is a multinomial distribution, problem number 20. So, this is a multinomial distribution where W can be written as N factorial by N 1 factorial, N 2 factorial, N 3 factorial up to N R factorial. So, there are this N is partitioned into R groups basically. So, if it partitions into 2 groups, then we call it binomial, because there are 2 groups, and if there are like more than 2, then call it multinomial distributions. So, the question asks us to show that this multinomial distributions, when you maximize it, when you maximize the W, the maximum value will correspond to N 1 plus N 2 and N 3 all as equal to N by R. Now, how do we approach that particular problem? So, we have already derived the case of W when or maximized W when we had a constraint of total energy and total number of particle, but in this case there is no energy constraints present and only the constraints of particle present. So, here we have to maximize W under the constraint that N 1 plus N 2 plus N 3 plus N R is equal to N. So, let us do that. So, W is n factorial by product of I equal to 1 to R n I factorial. So, we have to maximize W, ln W, and the sum of n I is n, where I goes from 1 to R. That is the constraint that we have to satisfy. So, as you know in our derivations when you did that, so we have to maximize ln W. So, we have to do del n I under the constraint alpha, that sum over n I is going to 0. So, as you know that alpha is a Lagrange multiplier, Lagrange's undetermined multiplier. We have to determine the value of alpha such that this quantity holds. So, we are maximizing the W, however, we are constraining the value of n I. So, first we will do or rather, so you have to maximize W under the constraints of n I. So, for that, as you know that we can write dW or d, it is better to maximize ln W instead of W. So, we are going to write d ln W as del ln W by del n I d n I. So, any exact differential you can write as sum over these quantities I equal to 1 to R. Similarly, we can also vary the n i's. Remember, n I is nothing but n 1, n 2, n 3 and all. So, you can vary n 1 or vary n 2 or vary n 3, whatever you might vary, the sum or rather each variations together is going to be 0. So, now the quantity that you have to satisfy is del ln W by del n I d n I plus alpha d n I is equal to 0, or I goes from always 1 to R, here also I goes from 1 to R, or del ln W by del n I plus alpha d n I is going to be 0. So, which means we have to show that del ln W by del n I plus alpha is equal to 0. We have to show, not show, but we have to use this particular constraint, use this particular formula in order to show that it is equal to 0. Now, let us do that. Now, what is ln W? Ln W is ln n factorial by a product of I goes from 1 to R in I factorial, which is ln n factorial minus sum over I equal to 1 to R ln n I factorial. We have discussed that before. So, I am just going little bit fast on this. Now, let us do del ln W by del n I. Before I do that, I have to just satisfy some more things. Let us just use the Stirling's approximation right here itself. That will be n ln n minus sum over I equal to 1 to R n I ln n I plus sum over n I, which will give us n ln n minus sum over I equal to 1 to R n I ln n I plus n. Plus and minus will cancel, giving us n ln n minus sum over I equal to 1 to R n I ln n I. Now, so this equation I will just give as 1 because that is very important. Now, this equation I can write in two parts, 1 and 2, or 1 minus 2, because that is in minus. So, let us put as 1 minus 2. Now, we will do that separately. 1 is n ln n. So, we have to take the derivative, therefore, del n I of n ln n. How do I do that? Let us see. It is a differentiation for a product. So, let us do step by step. It will be ln n del n by del n I plus n into 1 by n into del n by del n I. Now, ln n del n by del n I, you know that n equal to n I n equal to n 1 plus n 2 plus n 3 plus n 4 plus n 5 and all that, right. So, among whichever is matches with I will be 1 and the rest of them will be 0. So, therefore, it is nothing but ln n. Right hand side this will cancel and this one also will give us just 1, rest of the term will go to 0. So, it will be ln n plus 1. Now, let us do the other one. This is n I ln n I. Now, in this case we can write the sum, because I is a dummy variable, we can write the sum as j itself instead of I. Let us write as j, because that will be helpful. Now, we are going to do the derivation of that, and that will give us sum over j equal to 1 to r. So, del ln nj del nj by del ni plus nj, then I have to take the derivative of ln nj. So, it will be 1 by nj and again del nj by del ni, and the sum is over the whole thing. Then j equal to 1 to r ln nj. Now, this quantity, what will be this quantity? So, you see the j can vary from 1 to r and I am dividing with some particular I, let us say that is 2. So, only when it is del n 2 by del n 2 it will be 1, rest of the time it will be 0. So, it will be just one quantity which is nothing but I. This is typically called Dirac delta Kronecker delta function I j, but we are not going to go into that detail. So, that means the sum will be now replaced by just one term which is just ln ni plus same thing will happen here also, because here only the ith term will survive, everything else will go, and this is nothing but 1. So, we are going to get just 1. So, remember this is the first term and second term. So, from 1 minus 2 we get ln n plus 1 minus ln ni minus 1, 1 cancels, giving us ln n by ni. Now, this one we got it from this quantity, this particular equation ln w. So, we have maximized ln w now. So, this we have done now, plus alpha equal to 0. Now, we are going to put it back there. Now, that means ln n by ni plus alpha is equal to 0, which is n by ni is equal to minus alpha, or ln n by ni, or ln ni by n is equal to plus alpha, or ni by n is equal to e to the power alpha. Now, we know that if we sum over, so this is nothing but probability. So, if you sum over ni by n, we are going to get 1. So, which means if we sum over alpha, and the sum goes from again 1 to r, 1 to r. If you sum over e to the power alpha, we are going to get 1. So, take the e to the power alpha common, because it is nothing but a constant, it goes from 1 to r, this is nothing but just 1 is equal to 1. So, there are r terms there. So, r into e to the power alpha is 1. So, therefore, e to the power alpha is nothing but 1 by r. Now, coming back here, what you got, e to the power alpha is 1 by r. So, ni by n is nothing but ni by n e to the power alpha, or nothing but 1 by r. So, ni is nothing but n by r, and that proves the result. So, you saw that if there is no energy constraints, then the populations will be equally distributed. If there is an energy constraint, that means apart from alpha there is a beta constraints, then it will become exponential. So, you have done both when there is no energy preference, the population will be equally given, otherwise it will be an exponentially distributed. And we have seen that from exponential distribution, if the populations are equal, it will again go back to. So, we can show that as well. You know that for a Boltzmann distribution, ni by n e to the power minus beta e I by sum over e to the power minus beta e I, or e to the power minus beta e I by q, that we know, right. Now, if all the e's are same, they have the same value. If all e i's are same, let us say e I is equal to e 1 is equal to e 2 is equal to e 3 and things like that, then you know that n I by n, it will be simply e to the power minus beta e by sum over e to the power minus beta e I goes from 1 to r. Now, this is common. So, we will take it common, e to the power minus beta e to the power minus beta e sum over I equal to 1 to r with 1, that is nothing but 1 by r. That is much easier proof, starting from a Boltzmann distribution, but we wanted to do that without knowing Boltzmann distribution, and therefore, we arrived at that value as well. Okay. So, now going to the next question. Consider Stirling's approximation for ln n factorial in the derivation of Boltzmann distribution. What difference would it make if a cruder approximation of n factorial equal to n to the power n is taken? So, now you see that W is n factorial by ni factorial product, we have just seen that. So, ln W is ln n factorial minus sum over I equal to 1 to r ln n I factorial, we have done that, right. Now, here we are going to use both Stirling's approximation and the cruder approximation, I am going to see what happens to ln W. Now, using Stirling's approximation, what do we get? Ln W equal to n ln n minus n minus ni ln ni plus ni, which gives us n ln n minus n minus ni ln ni plus n, and n cancels each other, giving us n ln n minus ni ln ni. Okay. Now, use crude approximation, which is mentioned here. So, then in that case, we will start from here. Ln W is equal to ln n factorial minus sum over ln n I factorial I equal to 1 to r. Now, here we have to use n to the power n, right. So, ln n to the power n minus I equal to 1 to r ln n I to the power n I. Once we do that, we can write n ln n minus sum over I equal to 1 to r n I ln n I. Now, you can see that this cruder approximation is exactly same as the Stirling's approximation for ln W. So, Stirling's approximation gave us n ln n minus sum over n I ln n I, cruder approximation gave us exactly the same thing. So, therefore, this cruder approximation would perfectly be all right. The reason is that when the number of particles are very large, see where is n factorial is used, where we are placing the ball in the boxes without replacement, and when it is to the power, when you are placing the ball in the box with replacement. Now, when the n is very large, then those approximations actually become equal, and that is the reason here that Boltzmann distribution will exactly follow even if a cruder approximation was used as n to the power n. Another interesting question. Suppose that energy of a particle can be represented by the expression E z as a z square, where z is a coordinate or momentum and can take on values from minus infinity to plus infinity. Show that average energy per particle of the system of such particles subjected to Boltzmann distribution, Boltzmann statistics is kT by 2, and there is a hint also is given, and from the above result discuss equiposition theorem. You know that in order to calculate the average energy of a system E, we have to write the probability, first of all the energy Z and the probability and dz. That is what we have to do. Now, okay. So, Pz and now we write that it is going from minus infinity to plus infinity. So, it is a z square, and what is Pz? Pz is e to the power minus E z by kBt divided by integration of e to the power minus E z by kBt dz, and here we are going to get dz. So, this is our Pz, as you know, this is the Pz. Okay. So, so now we have in place the formula of the equation. So, let us write down the numerator and denominator. So, numerator is minus infinity to plus infinity a z square e to the power minus a z square by kBt dz. Take a out, it is z square e to the power minus a z square by kBt dz. Now, here we are going to use help from the hint and take and use the standard integral formula. So, that is, let us see what it says is that x square e to the power minus a x square, x here is z, is root over pi by 2 a into root over a. Now, here a is a by kBt. So, we have to write a by kBt into root over of a by kBt. Is it all right now? Let us see. Yep. So, here using the formula we have seen that z is nothing but x and a in the formula is nothing but our a by kBt. So, now it is okay. We can cancel this a and we can write as root over pi by 2 root over a and here kBt by 3 by 2. Okay. Now, denominator is a simple Gaussian integral minus infinity to plus infinity e to the power minus a z square dz. Now, what is the value for that? You know that we have already discussed that if that is the case, it is nothing but root over pi by a. So, root over pi by root over a, again here this will be kBt for sure, e by kBt, right. Here again it is root over a and root over kBt, because here a is nothing but a by kBt. So, now numerator by our denominator will become root over pi by 2 into root over a and kBt and root over of kBt divided by the denominator. So, root over a will go and root over pi and root over kBt will be here. So, kBt and kBt cancels, root over a cancels, root over pi and root over pi cancels, giving us half kBt. So, you see now, so the first part is done. So, average energy is half kBt, and where did we obtain from? We obtained from the energy where E z is written as a z square, and this type of energy equations typically called a parabolic potential, and it comes from it's called a quadratic potential, parabolic or quadratic potential, and this particular potential gives rise to, as you can see, half kBt of energy. So, equivalation of theorem says that every quadratic energy will contribute to half kBt. So, if there is a motion along x, y and z directions independently, it will contribute to half kBt plus half kBt plus half kBt, giving rise to 3 by 2 kBt. Now, so basically every degrees of freedom will give rise to half kBt. So, if you have n particle, typically there will be 3 n minus 6 vibrational degrees of freedom, each of them will give half kBt. So, each degrees of freedom will give you half kBt. So, there are 3 n degrees of freedom giving you half kBt each. So, for a system of n particles non interacting, and the equivalation theorem will tell you that the energy of the system is 3 by 2 n kBt.